As we push for the higher productivity and lower carbon footprint, integration with direct reduced iron or DRI into our blast furnaces body is no longer a luxury. It's a process necessity. Today we are moving beyond the what and into the how of mathematical matrix integration. By the end of this session, you will gain three core deliverables. First, a master level understanding of out of matrix pre-calculation for the top segment variable. Secondly, the ability to restructure Fe, elemental and enthalpy balances to account for unreacted descent. And third, the foresight to predict how these adjustments shift your raft and top gas thermal profile, which is very important. So, look at the wireframe furnace on the right of your screen. We are not just dumping material in the top, we are mathematically accounting for every atom and joule from the top gas matrix down to harsh thermal output. Understanding this integration is the key to stabilizing your furnace while cutting coke rates. To model this accurately, we must first define the physical and thermodynamic boundaries of the DRI itself. So before we touch the matrix, we have to define our inputs. On the left, you see a cross section of a DRI pellet representing our dry basis mass composition. A dominant 93% metallic Fe with 2% carbon, 2% oxygen and a small gang load of silica and alumina. On the right, notice the enthalpy waterfall chart. This is a critical for your senior managers or engineers to grasp. We start at entry state of 25 degrees centigrade with an enthalpy of zero point 0.8 megajoule per kilogram. As the material descends to the chemical reserve zone at 900 or 930 degrees centigrade, the enthalpy shifts to 0.148 megajoule per kilogram. These are not just numbers, they represent the sensible heat injection we are introducing into the bottom segment. By precisely calculating this enthalpy, we can determine the exact so what factor, how much thermal energy we are effectively stealing from the ascending gas to prepare the burden for the hearth. But for this enthalpy shift to work in our model, we must establish a firm assumption about the material behavior during the descent. So follow the gray arrows in the furnace diagram. We specify that DRI pellets are neither oxidized nor reduced during their descent during the top segment and the chemical reserve zone. We lock the mass and composition at the top and carry it down to the 930-degree boundary. Why? Because if we assume 95% of the oxygen has already been removed in a shaft furnace, the kinetics of further reduction in the blast furnace top segment are negligible compared to the nominal condition of raw material in conventional blast furnaces. The visual here shows a locked icon halfway down the shaft. This indicates that while the enthalpy is changing as it heats up, the mass of Fe, carbon and silica remains constant until it hits the bottom segment. This allows us to use a fixed 80 kilogram charge per ton of hot metal as a stable baseline for our matrix calculation. Now that our assumptions are locked, let's look at the actual architecture of the matrix integration. The challenge with the DRI is that the charge amount is uh, basically is a variable in the top segment, but our calculation usually flow from bottom segment up. To solve this, we use out of matrix precautions. We define the top chart DRI quality and quantity, say 80 kilograms, and inject it into bottom segment matrix as a fixed variable before the standard equation resolve. The flow diagram shows a standard matrix flow on left being bypassed by this DRI integrated flow on the right. Step 1 defines the variable, step 2 passes it to the bottom, and step 3 the top connection perfectly balances the intermediate boundary. This bypass is essential for senior engineers to understand because it prevents circular reference in your spreadsheet while ensuring that the 1000 kilogram of Fe produced in the hearth is accurately sourced from both ore and DRI. So with the architecture in place, we can now restructure our core mass balance equations further. So let's get into the metallurgy. So the visual display, the revised Fe mass balance equation, 0.93 times the mass of DRI pellets descending plus 0.768 times the mass of FeO uh, 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 into the bottom equals our 1000 kilogram Fe product. Notice the arrow pointing to the 0.93 coefficient, that is our 93% Fe specification. The operational impact here is profound. Of your 1000 kilogram of hot metal iron, exactly 74.4 kilogram is now supplied by the unreacted DRI. This drastically reduces the load on your standard ore, meaning less oxygen needs to be stripped and less carbon is required for reduction. You are essentially preloading the hearth with a metallic iron which significantly alter the chemical kinetics of the lower furnace zone. We are no longer just managing reduction, we are managing a melting process for a portion of our burden. Iron is not the only thing that we balancing. We have to account for the gang and the carbon also as well. So it is also very important. Coming to the bottom segment elemental balancing. Here beyond the iron, DRI brings its own chemistry into bottom segment. The diagram shows four distinct paths flowing from an 80 kilogram DRI input into our matrix row. Path 1 is the carbon at 2%, path 2 is the oxygen at 2%, path 3 is the silica at 2%, and path 4 is alumina at 1%. These values are typed directly into the cell AH7 through AH16 of your matrix. Why does this matter? Because every gram of silica in the DRI is a gram of silica that is not coming from higher gang or our coke. By tracking this path, we ensure that our slag mass calculation and our carbon out specification remain airtight. We are mathematically ensuring that the carbon in the DRI is credited towards the final hot metal chemistry. Further reduction or reducing the reliance on the coke as the sole carbon source for the processes. Accurate elemental paths are necessary, but the real driver of the furnace stability is the enthalpy injection. So this is where the thermodynamics gets interesting. So look at the visual of DRI pellet crossing the thermal boundary at 930 degrees centigrade. It carries an enthalpy of 0.148 megajoule per kilogram. We include this as a specific term in row 21 of our matrix. The inside box at the bottom is the key because the DRI enters the bottom segment already heated to 930 degrees centigrade. The bottom segment enthalpy equation must actively account for this sensible heat. This directly reduces the endothermic reduction energy burden on the raceway. Think of it as a thermal gift to the hearth. We have used cheap top gas energy to heat the planet, which means we need less expensive carbon combustion at the tuer to achieve our final 1500 degrees centigrade molten iron temperature. This is a massive driver for the fuel rate reduction. So to see how we capture that cheap energy, we have to analyze the top segment dynamics. So, so to model the top segment, we use a two-flow approach. On your screen, you see flow 1, the solid pellet entering at 25 degrees centigrade, and flow 2, the pellet descending out at 930 degrees centigrade. The matrix logic here is elegant because mass and composition do not change, but the temperature and enthalpy do. The matrix requires two distinct columns. One bring the mass in and other immediately take it out, leaving only the thermal footprint behind. So this perfect balance ensure that our Fe, C and O balances in the top segment remains zeroed out. While the enthalpy delta is fully captured, it is a mathematical trick that perfectly mirrors the physical reality of unreacted descent through the shaft. This thermal footprint is what ultimately dictate our top gas temperature and energy efficiency. Now look at the gas solid heat exchange. So the blue ascending gas arrows meet the gray descending DRI arrow. We calculate the top gas temperature by adding the 25 degrees centigrade entry enthalpy and subtracting the 930 degrees centigrade exit equivalent. The key finding here is the enthalpy delta, the difference between 800, 0.800 and 0.148 megajoule per kilogram represent the precise amount of thermal energy the DRI absorbed from the ascending gas. As a manager, you should recognize this as an efficiency gain. We are using the latent heat of the top gas, which would otherwise be lost to the scrubber to perform work on the burden. This cooling effect on the top gas is a direct indicator of improved furnace efficiency, provided we stay above the AC dew point. With the math settled, let's look at the real world operational impact, starting with the economics of the feedback. So coming to the data, here is clear and linear. On the left, coke requirement graph shows a steady decline as DRI input increases because DRI contains 93% Fe. Very little reduction and thus minimal coke is required to convert it into molten iron. Similarly, the iron ore requirement drops significantly for every 1000 kilo of Fe produced. 74.4 kilogram is now pre-supplied by that initial 80 kg DRI charge. This is a direct replacement of raw ore with a pre-reduced metallic. For your plant managers, this means a lower ore to coke ratio and a significant reduction in the total fuel rate. You are essentially buying a productivity by shifting the reduction work from the blast furnace to the shaft furnace where the DRI was made. Beyond the feedstock, we are also a massive shift in our environmental and aerodynamic profile. So let's talk elemental compliance and furnace speed. The top graph shows the CO2 driver metallic Fe bypasses the carbonaceous gas production cycle entirely, leading to a noticed drop in emission pattern of hot metal. But look at the operational bonus on the bottom. Less coke consumption means significantly less blast air and therefore less nitrogen is force through the tuer. This reduces the top gas volume. Now question arises, why is this and what is so what factor? Because the lower gas velocity permit us to accelerate molten iron production rate without destabilizing the furnace aerodynamic or hitting the flooding limit. This is why companies like AK Steel and West Alpine have integrated DRI. It's also about pushing more ton through the same hearth. Even our byproduct chemistry is optimized specifically in the slag. Now coming to the operationalization of slag management, which is often a afterthought, but not with the DRI. A standard ore contains about 5% silica while our DRI contains around 2% silica. By replacing a portion of the ore with the DRI, we are inherently starving the slag of silica. This effect is accomplished by our lower coke requirement as coke itself introduces significant silica, about 7% into the system. The result shown in the curve on the right, on the rather left, is a total lower slag mass generated per ton of hot metal. So less slag means lower flux requirement, lower thermal losses to the slag and more room in the hearth for iron. We are streamlining the entire chemistry of the furnace, reducing the dead weight of gang material that we have to melt and manage. However, all these changes culminate in a significant shift in the furnace thermal profile. So, this slide is a warning for your tuer operator. The integration of DRI causes a drop in both top gas recovery flame temperature. Top gas temperature falls by 14 degrees centigrade over 100 kg of DRI because there is a less hot gas rising to hit the charge. More importantly, the raceway flame temperature or the raft drops by about 10 degrees centigrade per 100 kilogram of pellet. So this is a conservative consequence of the reduced coke combustion in front of the tuer. While a cooler furnace is generally more efficient, you must monitor these closely to ensure you maintain enough high temperature heat for the endothermic reaction in the dripping zone. It's a delicate balance between the fuel efficiency and maintaining the thermal reserve to the very specific. To summarize these impacts, let's look at the diagnostic master matrix. So coming to the this slide where it's basically here is your actually cheat sheet for the control room. We have standardized the data per 1000 kilogram of Fe in product, moving from a baseline of 0 kg of DRI to our 80 kg integrated model. Every key metric moves in the right direction. Coke and ore requirement down, CO2 emission down from 720 to 675 or 672 kilogram. Top gas nitrogen volume down from 910 to 855 kilogram. Slag mass down, even the raft shows a controlled descent from 2105 degrees centigrade to approximately 2097. All these deltas are driven poorly by the integration of 93% metallic unreacted DRI into our mass and enthalpy balances. This is not just theory, it's a quantified roadmap for the furnace optimization. If you are not seeing this shift in your model, you haven't integrated the matrix correctly. Finally, let's look at the big picture, the causal loop of integration. So we close with the causal loop. Everything we have discussed is interconnected. It starts with the input 93% uh, of Fe and low silica DRI. So this reduces the reduction energy needed, which decreases the coke demand. Lower coke combustion require less blast air, which lowers total emission and gas velocity. This in turn restructure the thermal profile also, altering the flame and top gas temperature. The closing insight is this: the integration of top charge DRI is not a localized adjustment, it's a holistic system optimization. The mathematical matrix we have built perfectly mirrors the physical efficiency gained in the furnace.